The extension to the Polish national flag problem is the Dutch national flag problem. The Dutch national flag problem is the original problem, actually, proposed by some Dutch guy. I forget his name, but Dijkstra, who was also Dutch, popularized this problem by incorporating it into one of his books in the 1970s. And um, when Quicksort, actually, let's look at this problem and then we'll see how it's useful in case you don't remember. So, like the Polish national flag problem, it's the requirement is the same, except that we have three colors in the flag. So, what we need to do is take the given array. So, the given array will have the numbers in a scrambled order. So, some of them might be red, the reds might be here, the whites might be somewhere else, and the blues might be like this. And so we need to transform this array or the elements of this array in a way that we get all the reds to the left, all the whites in the middle, and all the blues on the right side, so that the colors of the Dutch national flag are clearly seen. And the requirements are the same. This needs to be done in one pass, single pass, linear time, and using no auxiliary space beyond, few variables. So again, the Polish national flag problem is the two-color version. The Dutch national flag problem is the original three-color version of the problem. In the problem set that you were given, for some reason, the three colors are R, G, and B. Okay, not R, W, and B. Let's think of them though in terms of R, red, white, and blue. So I'm going to do exactly what I did in the previous problem, which is to use a decrease and conquer approach. As a lazy manager, I assume that if I were to ignore the rightmost number, that's the only number I'm going to look at. I'm going to assume that the subordinate that I hired under myself has already solved the problem for the prefix up to index n minus 2. So red, white, and blue. Uh, this is already uh, the, the prefix of the array has already been painted in this particular order. So I have to now decide what to do with the last number here. So if this last number or if the last color is blue, I don't have to do anything. If the last color is white, the last color is white, I want the white region to be contiguous. So if I assume that as before, we have a red pointer pointing to the rightmost, red number, white pointer pointing to the rightmost, white number, and if you like, you can think of the pointer that the lazy manager is using, the I pointer, or you can think of it as the blue pointer if you wish. But uh, this manager sees a white number and we know that this white number has to go over here. So what do? We ask the white pointer to take one step forward and we swap whatever number that is, it's the leftmost blue number actually, with the white number. So that will make this white and this blue. And thereby extend the white region in a way that the ordering of the colors is maintained. So that's what we do if the rightmost number was white. But what if the rightmost number was red? That's the third possibility. Um, well, if it was red, um, I could try to swap it with the red pointer, but that would make the white that would make a white number appear again to the left. So, I mean, we could go that way, but I'll do something else. First, I will pretend that this red number is actually white. So I'll do exactly what I did in the previous step, which was, so my goal is to take this red number and it needs to reach here to extend the red region, but the white region and the blue region should shift by one place to the right. And instead of doing this in one hop, you can do this in two hops. It's like a ball that bounces once and then reaches the destination. So what if I exactly copy and paste the same code that I wrote for what to do when I had the number being white instead of red? So the white pointer would step forward and then we would swap these two values. In that case, this value would become red, this value would become blue. So at least the blue region is now good. But I know that this value is red. So it's not in its right place. So here I can now ask the red point. I can do the same thing with the previous two pointers. Instead of blue and white, I do the same thing with white and red. The red pointer moves one place forward, and these two, the red and white pointers, swap their values. So this value becomes red, and this value becomes white. So this means that we have the same uh, three regions painted and extended such that the rightmost red number is uh, where the red pointer is, the rightmost white number is where the white pointer is, and the rightmost blue number is where the eye or the blue pointer is. That makes sense. So we write the code essentially in the same way. Um, I had, I was depending on my subordinate to have solved the problem on a prefix of size n minus 1. My subordinate depended on his or her subordinate, and so on. At the leaf level, this worker would have relied on problem of size 1 and would have focused only on the leftmost number at index 0. Their manager, his or her manager, would have focused on the number at index I equal to 1, and so on. I focus on index n minus 1, my subordinate would have focused on index n minus 2, and so on. Now the work is done in a bottom up way because I first rely on my subordinate to do his or her work before extending the solution uh, to a slightly larger subproblem. So this is the order in which work is done, which means we could write this in an iterative way using a for loop where I varies from 0 to n minus 1. The body of the for loop is describing the work to be done to handle array of I. I don't know if it's called array balls. It's called balls. So balls of I. Okay, so that's the structure of the code. Let's write the code. Why don't I write it? Okay, let me write it on the next page. So I have my index I varying from 0 through n minus 1. What is the work I should do to handle balls of I? Well, if it's already blue, I don't need to do anything. So if it's white, then I have to do what I did in the Polish national flag problem. So if balls of I is white, okay, turns out that in the IK problem, it's not, instead of white, for some reason, they've chosen the color green, but let's treat it as white for our purposes. Balls of I is white. What do? We ask the white pointer to take one step forward. And then we swap. Let me just say swap balls of white with balls of I. And that will fix things. That will fix the white and blue regions uh, in the right way. The most complicated case is when balls of I is red. In that case, we need two swaps to get this red ball or red color into the right spot. The first step is actually identical to what we did here. So I could literally copy paste that same code. Swap balls of white with balls of I. So the white and the I pointer, which I like to think of as a blue pointer, these two have adjusted themselves by this stage, but the problem is that the number here is red. Right? So it needs to be sent there, just like I described a couple of minutes ago. So the red pointer and the white pointer will do the same thing which the white and the blue pointers were doing. Namely, the red pointer will take one step forward, and then we'll swap the red pointer and the white pointer. And that fixes things, as we saw. How are these pointers going to be initialized? Well, when we start at I equal to 0, there is no painted region on the left. So the rightmost white number doesn't exist. The rightmost red number doesn't exist. So we initialize both to -1. And this essentially is the code. I don't know if you have to return something. Modify the array in place. Return type is void. So this should make it run. So as you see, whether we look at this piece of code or the Polish national flag problem, we have a simple for loop, and with the body of the for loop takes constant time to run. So it's overall linear time, just a swap or two, and it doesn't use auxiliary space, modifies the array in place.
So if it's blue, we're not doing anything with it.
Yeah, because
You just
it's as if our I pointer is the blue pointer. It's already, the blue region is already on the right extreme, so we don't have to do
Yeah.
anything.
So by leaving, eventually it's all going to stay in the middle. Then. I'm sorry,
What?
it'll be at the end. Sorry.
Yeah, yeah.
Yeah.
Okay, let's see. Soumya Acharya.
Hey, Omkar. I remember this problem came sometime like in sorting test or somewhere.
Hmm.
So how we solve? I mean, there is another way of solving this problem is kind of like keep a index, which like keep three index: start, end, and index, and then keep on moving the index. And if we encounter R, then we basically throw the start to the index and mark start as R and keep on moving the index. And do the same if we encounter, uh, I think RGB, right? If we encounter the B, so it is
Hmm.
the end index. So we throw it to the end index and move the index forward. So eventually, if we keep on doing that, this gets sorted in that pattern.
Maybe, yeah, maybe. I mean, you could very well be right. I don't think about, so the way you described it, right? I My brain doesn't um, process solutions that way. Uh, that's why described it in terms of these colors and a decrease and conquer strategy. So it's quite possible that what you're the way you described it could be an alternate way of doing it. I won't dispute that, but uh, for me, this is decrease and conquer. Right, the code is something that just arises out of that.
Mm.
It's not. I'm not thinking in terms of the code here. I'm thinking purely as a decrease and conquer strategy. What do I do with that rightmost number or color? How do I handle it?
Yeah, sure.
Vasan?
Yeah, okay, yeah, I think with group the numbers in the pattern it matches because when I solve these problems, I solve them differently. Both the RGB one and this now with your approach, both can be solved with the same method. I used the switch case when I did the Dutch national flag. Kept three, as the previous person was saying, three indexes mid, low, and high, and then R and B would increment the mid and low, and the BA
Okay, I
would,
guess, yeah, maybe that's
yeah, that
probably
was
closer
very
to horse
confusing.
partitioning. Is that, would it be closer to horse partitioning,
Similar
the
to
way?
horse, I think. Yeah, but this will match the same Lomutos. I did the Lomutos for the group the numbers, but this I couldn't follow the same method because I was not sure. No, it doesn't
Yeah, I mean,
match.
I always say in the class that Lomuto's partitioning is better to use. Um, and this is why, because it's a straightforward extension from two
Correct.
colors to
I
three
couldn't use it
colors,
that day. Yeah,
or two-way partitioning to three-way partitioning.
correct, correct. I couldn't solve it. I asked it, so I just did the first fix I did. Thank you.
Okay, Sayed.
Yes, hi there. So I understand the logic. Only in this code, we are looping from I from 0 to n minus 1, but in our logic, we are going from I from the right side towards our left. So isn't
The
it like
logic, so
from
that's
n
just the
and
delegation, right?
from
So
n minus 1 to uh,
in the logic, what I said is, if I am the lazy manager, I'm focused on this number.
mhm.
I first rely on my subordinate to solve the problem on size, an array of size n minus one. My subordinate, before he or she does that work, is first going to rely on their subordinate to solve the problem on an even smaller size. And so there is a chain of delegation going down all the way up to a leaf level node. And that's where the work actually
Okay,
starts.
okay.
The leaf worker starts the painting job, and then successively up the chain, each manager is extending the painted region by one more element. And so that extension is actually going from left to right, from I is equal to
Yeah,
0.
okay. Yeah, got it. Because it's a bottom up approach, so it's going from 0 to n minus 1.
Yeah, it's
I
bottom up.
understand.
That's why it works in that way. I could write this recursively, but there's no point because
I got it.
there's
Yeah, I understand. Clear. Thank you.
Uh, Abhishek,
Hi, Omkar. So, two quick questions. How long can we extend this approach? Like until how many pointers? Is there any upper limit
any
on
number
that?
of pointers, 4, 5, 6.
Okay.
Just have to, the number of bounces in the middle will
Mhm.
be more, that's all, until you get the number in the right final spot.
Understood. And the second question was, so the motivation around taking two hops is just to make sure that the code remains exactly
Sorry,
same.
just 1 second. You can extend this easily as long as you use Lomuto's partitioning. When you start using horse partitioning, then
Right.
it's
Makes
not
sense.
as straightforward. Yeah, go ahead.
Right. Understood. And the second question was, the motivation around taking two steps is just to make sure that the code structure remains the same, right?
Yeah, yeah,
Okay.
yeah. You could have done it some other way, but I just want the code structure to be similar. Yeah.
Sure. Makes sense. Thank you. Thank you, Omkar.
And this, by the way, handles all the edge cases. So if one of the regions is blank, um, it would still work.
Right. Mhm.
Or if two of the regions are blank, it would work even then. Sayed, did you have something more to ask?
Sorry, I forgot to lower my hand.
Okay, Divya.
Hey Omkar. So I was looking at this problem to sort the integer array based on like descending order of frequency of the elements. The straightforward approach is good, but like to solve it in O of n time was one of the mock interview questions I had. Uh, I try like when I think about O of n time complexity. One thing was a quick select approach which I could take. The other
Hmm,
thing was like a counting sort or like a bucket sort kind of problem.
hmm.
um, but I wanted to see which class of problems or which topic this would come under. If it would be if I can use quick select for it, or how to go about approaching it was my question to solve it in O of n time complexity.
Yeah, quick select would be the approach. So,
Okay.
are you referring to? So there is a problem called top k frequent elements.
The question I got was sorted based on the frequency of the elements in the array. If at
Okay,
all elements have same frequency, then use the first occurrence in the input array.
I see. So if you have to do a full sort, then you wouldn't use quick select, because quick select is what would give you the kth most frequent or the top
Correct.
k frequent elements,
Yeah.
assuming they don't have to be sorted. So if you
Yeah.
have to actually do the sorting, then you might as well use a heap, or do an n log n sort where n is the number of uh, unique elements, right?
That
With
would
their
be end login, right? Yeah.
Yeah, so it would be n log n, but it would be at least based on. So first you would compute their frequencies,
Mhm.
and then you would sort each element. You would sort the element comma frequency pairs
Right.
in decreasing order, and you're saying you have to do the full sort.
So I couldn't think of a way without doing the full sort, which I thought would be n log n,
Hmm.
which is where I was stuck. How to get to n solution?
Yeah, getting to n is only possible if you use quick select, in which case they should not be
Yeah.
asking the full sort. They would be asking the kth most frequent element or something like that, or
Okay.
the top k frequent elements, one of these two.
Okay. Yeah, that wasn't the case. Okay, I'll try to
Yeah,
ask
just check what
ops
the
maybe
question
if they
was,
can.
and again you can ping me if it's not
Sure.
clear.
Thanks. Yeah.
Abhinav.
Hi, Omkar. Can you hear me?
Yeah.
So when we are implementing quick sort, we should use three-way partitioning, right? And should we
Quick
use
sort and
this?
quick select both, ideally, but if you're not having time in an interview, you can just confirm with the interviewer that two-way partitioning is okay.
And so suppose I am implementing three-way partitioning. Usually what I do is I use left pointer and right pointer. So should I try this approach? Like white space is the pivot and uh,
Yeah. So what you would do is, uh, so for three-way partitioning, you would need three partitions. The left one has values less than the pivot, the middle one has values equal to the pivot, and the right one would have values more than the pivot. Right? That's
yeah,
how you want to sort it.
yeah,
So what you do is, again, you pick a random pivot,
okay,
but in two-way partitioning, what you would do is you would move that pivot to the left and then
yeah,
paint the remaining region and then finally put that pivot back into its final place.
yeah,
Here, you just note what the value is of the middle element. I mean, sorry,
yeah,
the random pivot. You don't have to move it anywhere because there can be multiple copies of that pivot. So in that case, what you do is exactly what we did in the Dutch national flag problem. You have three regions: a red region, a white region, and a blue region. And you have a blue pointer or an I pointer, you can say, going from
yeah,
0 to n minus 1 again. And if the value, the current value, is blue, then there's nothing to be done.
yeah,
Right? In other words, if this value is more than the pivot, nothing to be done. Else, maybe the value is equal to the pivot. Right? In that case, you will do exactly what we did: white plus plus, and then swap A of white with A of blue.
yeah,
And in the third case, if if that number is smaller than the pivot, that means it's red.
yeah,
So we would take this, exactly copy it here, and in addition to that, we would have the red pointer doing the same thing. Swap A of red with A of white. Red and the white pointers do the same thing which the blue and the white were doing. So
okay,
this would make the red pointer come here, the white pointer come here, and the blue pointer or the I pointer is obviously at the end. How many copies of the pivot are there? White minus red.
yeah,
There has to be at least one copy because you looked at that value, right? When you pick the
yeah,
random pivot index, you looked at that value, so you know it has to be one, but there could potentially be many. And so when you recurse on both sides, you recurse only obviously you don't recurse in the middle partition. When you recurse on the left side, you're recursing from start
till red,
up to the red value. And then you're recursing
okay,
from white plus 1
till
till
end,
end, till the end. Those are the two partitions you recurse on. And remember, the place where three-way partitioning is particularly useful is when there are lots of copies of the pivot. So that way the middle region becomes really fat and inflated, and the red and the blue regions are very, they shrink down to very small and something very small in size. And so when you recurse on them, your depth of the recursion tree will not be much. Quick sort will quickly terminate when there are lots of duplicates.
okay.
Sarabjit?
Thanks, Omkar.
Sure.
So, just talking about the three-way partitioning for the Dutch flag, you have to assume that you always have to have three colors, and that the colors are equal in number. Or will it also work
It
for?
works even if they're not equal.
I see.
Yeah.
Okay. Okay. Great. But you have to have three colors.
3 colors, yeah. This
Got
can be extended to 4 colors
Yeah.
or 5, but I haven't seen that kind of problem. But if you use Lomuto's partitioning, you just have to, extend the same pattern for, just to do more swaps. If there are 4 colors, then there would be another else condition here where you would have, 3 successive, instead of a two-step uh, path to the destination, you would have a 3-step path to the
Got it.
destination.
Yeah. Thank you.
So, uh, okay, Vikas, last question, then I'll move ahead.
Yeah, yeah, Omkar. I didn't exactly understand. Like, can you go to the pivot thing that you wrote? So, how this code is different than the previous code that you have written? Like,
It's the same.
it's the same code, right?
Yeah,
So,
except that instead of comparing colors, saying the colors are equal, here the condition is more than the pivot, equal to pivot, or less than pivot.
oh, basically, we are working with the numbers here.
We are working with numbers, yeah.
Oh, got it. Okay. Okay. Thank you. Yeah.
So these were the 4 problems, and their lead code versions are given here. What I want to do uh, is in maybe the last 30 minutes is to also show you alternate ways of solving this problem, which I think are a little more complicated, but um, you could have still thought in that way.